to two projects. In this video, we are going to explain about the project that is HSoMLSDP, a hybrid swarm optimized machine learning framework for software defect prediction. So before getting into the execution, first let us understand what is this project about. Software is a key part of many modern systems, especially those that are safety critical, like in aviation, medical devices, or nuclear plants. In such systems, even a tiny software defect can cause serious problems, such as system failures, unexpected behavior, or expensive crashes. That's why it is so important to detect defects early. Doing so improves the reliability of the software, reduces the risk, and also saves the cost on fixing problems later. In past, people they relied on traditional statistical or probabilistic methods to predict where defects might occur. While these methods works to some extent, they often struggle to understand complex patterns or non-linear relationships. So here where machine learning comes in. Machine learning can automatically learn from past software data to detect patterns and predict defects more accurately. It is more flexible and powerful than traditional methods, making it a better tool for ensuring software is reliable and safe. So here, even though machine learning has improved software defect detection prediction, there are still some big challenges. One major issue is that performance of these models depends heavily on hyperparameters, setting that control how the model learns. Finding the right values for the hyperparameters can be tricky and time consuming. So there are existing optimization methods like meta-heuristic or swarm intelligence algorithms that try to optimize these settings. While they can help, they also have limitations. For example, they can be slow, get stuck in poor solutions, or perform inconsistently depending on the problem. So there is no single method works perfectly in every situation. There is clear need for better strategies. The goal is to make software defect prediction models more accurate, efficient, and reliable so they can detect potential defects with confidence. So to overcome with all such issues, this project it introduces a system called HSoMLSDP, which is hybrid swarm optimized machine learning software defect detection prediction. It is designed to predict software defects more accurately. At its core, it uses a model called Swarm Optimized Machine Learning Defect Prediction, that is SOMLDP, that combines traditional machine learning models like neural networks and XGBoost with the advanced swarm optimized, that is swarm based optimization techniques. So here, this optimization techniques helps the system automatically find best setting hyperparameters for the machine learning models, making them perform better without manual trial and error. In short, the framework intelligently tunes the models to improve defect prediction and reliability. So the main components of the proposed system are GFGOA ABC. So this combines gravitational force and bee colony strategies to help the system fine tune solutions better and search the results faster. So this is a hybrid swarm optimization algorithm. Then comes LFGOA ABC. So this combines a hoping strategy called levy flight with bee colony behavior to explore options more efficiently and speed up the convergence. Then we have the hybrid model. So using these hybrid algorithms fixes the problem of individual methods such as slow progress or getting stuck early, making optimization more effective. So these are the individual models. These are the individual optimization, hybrid swarm optimization models that are incorporated in this project. Then coming to SOMLDP. So here we use hybrid swarm algorithms to automatically find the best settings that are hyperparameters for the machine learning models. And here we will be training on historical software defect data like NASA datasets to learn patterns of the defects. So by refining the model hyperparameters through optimization techniques, it improves the accuracy and reliability of the software defect prediction. And here, to further improve the performance of this project, we are incorporating stacking classifier. So here we are incorporating stacking classifier, which is an ensemble approach, which combines three different machine learning models that are random forest, XGBoost, and decision tree. So by combining these models, the system takes an advantage of the strengths of each one, making it more robust and able to deliver more accurate predictions of the software defects than any single model could it own. That is, could it done by own. And to make the system interpretable, that is understandable, the project integrates explainable AI models, which are LIME. So it integrates LIME model to show which features of the input data are most important in making each prediction. And furthermore, to develop a simple web interface, here we have incorporated Flask. So we have developed a simple web interface in this project so that users can interact with the system easily and get the predictions. Here we have developed it by using Flask with the user authentication. So only secured users, that is registered users only, will be able to log in and do the interpretation, that is do the prediction part. Now moving on to the implementation. To implement this project, here we have followed the steps which are mentioned in the flow of work. So these are the steps. Let's understand how we have implemented. First, we have imported all the necessary Python libraries and the tools are loaded to set up the environment for data processing, modeling and optimization, visualization and web development. Then comes exploratory dataset part, where the dataset is examined to understand its structure, checking for missing values and get insights into the distribution of software defects. Then comes pre-processing. So here we clean the data set by handling missing data, that is by removing null values, and eliminate repeated entries to avoid bias, that is duplicate values, and outliers. We will be removing extreme values that may skew the model learning. Then comes data visualization. So at this stage, we visualize relationship between features to identify the patterns, and we examine examples of defect and non-defect modules to understand the data. Then comes label encoding. At this stage, we convert categorical data into numerical values so machine learning models can process them. Then comes resampling. So here we handle class imbalance by generating synthetic examples of defect-prone modules to improve the model training. SMOD is nothing but synthetic minority oversampling technique. Then comes optimization. So at this stage, we use various algorithms to tune the model's hyperparameters for better performance. So here we have used ABC, which is artificial bee colony, GOA, which is grasshopper optimization algorithm, and here comes LFGOA, which is levy flight grasshopper optimization algorithm, and here we have GFGOA, which is gravitational force grasshopper optimization, and here we have GFGOA, which is the hybrid model of GFGOA and this ABC model. So it combines both this hyperparameter tuning model. And here we have LF, GOA and also ABC. So it combines LF, GOA and ABC. So these three are combined together, which forms a hybrid optimization technique. And then comes separating the data set into features, that is X and the model input and the label Y for the prediction targets. And we will be splitting the data into train and test sets, where training set is used to train the model and test set is used to evaluate the model. After that, we will be training the models. First, we will be initiating the models and then we will be training the models. That is different machine learning models, including XGBoost, MLP, stacking classifier, using the optimized hyperparameters. So we will be training all the models using these hyperparameter, that is hybrid hyperparameters. And we will be evaluating all of them using accuracy, precision, recall, and FN score. After that, we will be visualizing them through graphs and we will be saving the best performing model for the future use. And we have done explainability, that is, we have used LIME technique to explain which feature contributed most to the prediction, improving the interpretability and the trust. Coming to the front end part, here we have developed front end using Flask framework, which includes registration and also login, supported by SQLite for data usage. And in the front end, users will be able to provide inputs and that will be pre-processed at the back end. It will be fed to the train model and the train model will be displaying the output. So this is how we have implemented. Moving on to the algorithms used. So these are the optimization algorithms that are used in this project. So here we have used artificial bee colony, GOA, LFGOA, GFGOA, GFGOA ABC, and LFGOA ABC. And these models are the machine learning models that are tuned with these optimization models. And this is the extension model stacking classifier, which combines random forest, XGBoost, and decision tree. And to implement this project, we need basically two kinds of requirements, which are hardware and software. In hardware, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Software requirements are application of Anaconda, primary language of Python, front-end framework of Flask, backend framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let's execute it. To execute, open the code folder that contains source code files. So let's open it. So these are the source code files of this project. Let's understand each of them. Here we have model folder in which we have algorithm information that will be loaded into the project code during runtime of the application. And here we have NASA defect dataset, which contains different files. So let's open it. And here we have original data. So here files are in these formats. So here we have CM1 dataset, JM1, KC1, KC3, KC4, MC1, MC2, MWPC1, PC2, PC4, and PC5. So from these, we will be cleaning the data. And here we have stored it in this file. So here we have stored it in this file. Okay, let's get back. And here we have process data. So here we have stored the process data in these 5 folders, where this folder contains CM1 data, this folder contains KC1 data, KC4, PC3, and PC4. Let's see the data which we have in CM1. So here we have all the files. Similarly, we will be having in all these folders also. Get back. And here we have static folder in which we have CSS, JavaScript, and Bootstrap files, which are important for the project's appeal. And here we have templates folder. This folder contains all the HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And here we have test cases that we will be using in the front end. Here we have app.py file. So this .py file contains the information related to front end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with a database, and generating dynamic content to be rendered in HTML templates. Here we have multiple Jupyter Notebook files. So these Jupyter Notebook files contain combination of code, graphs, and outputs all in one place, which allows users to write and execute code in the individual cells. So here in each file, so this Jupyter Notebook file, it loads the data of CM1 and does the prediction on that. Similarly, we have KC1, KC4, PC3, and PC4. And this is the signup.db file. This file is a database file which is used to store the user information. So this is all about the code folder. Now let's execute it. To execute, copy the path of the code folder from the address bar of the file explorer. I have copied it. Now open Anaconda prompt. It is open. Now give the command cd, give the space, paste the copied path, click on enter. Here, if you observe, current directory is changed to the code folder's path. Now compile app.py file. So give the command python space app.py and click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the localhost and the port unless configured differently. So this is the local host and this 5000 is the port. Now copy this local link provided by the Flask framework and paste it into any web browser. I've copied it. I prefer Google Chrome, so I will paste it in that. Paste the link here, click on enter. This is the web page of the project, which is displayed in the browser, and this is developed using Flask framework. So we need to get signed up. So first click on sign up, or else you can click on start prediction. So click on it. And first you need to create an account. I have already created, so I will directly sign in. So click on sign in. Give username and the password. We have signed in successfully and redirected this prediction page of this project. So let's start doing the prediction. Here we are doing prediction for PC3 dataset. So click on that. And here you can see multiple parameters which are need to be entered. So based on these parameters only, we will be able to predict the software defect detection. So first we have is the local blank. It's the number of blank lines in the code. It indicates spacing and readability, often used in metrics to measure code size. Then we have call pairs. It is the number of function or the methods calls pairs in the program. It helps to understand interaction between functions and the program complexity. Then we have log code and comment. It is the line of code including both actual code and comments. It shows the total size of the program along with the documentation. Then we have condition count. It is the number of condition statements in which code, that is like if or switch. Higher counts indicate more decision points and potentially higher complexity. Then we have cyclomatic complexity. It measures the number of independent paths through a program. It's a higher value. That is, a higher value means the code has more decision points and it is harder to test or maintain. Then we have cyclomatic density. It is the cyclomatic complexity relative to the size of the code. Normalizes complexity to account for program length showing complexity pipeline. Then we have decision density. It is the ratio of decision points to total lines of code. Helps to identify code that has high decision making to relative to its size. Then we have design density. So it is a measure, that is, it measures the complexity related to the design or the structure of the code. It helps to evaluate how design choices affect code complexity. Then we have essential density. It is a ratio of essential complexity, that is a core logic that cannot be simplified, to overall complexity. It indicates unavoidable complexity that arises from the problem itself. Then we have log executable. It is a number of lines of executable code excluding comments and the blanks. It represents the actual operation, that is operational portion of the program. Then we have parameter count. So it is the number of input parameters for functions or the methods. More parameters can increase the likelihood of errors and the complexity. Then we have Halstead content. It measures the size of the implementation in terms of unique operations and operands. It reflects the informational content of the program. Then we have Halstead difficulty. It measures the difficulty of understanding or writing the program. Higher values indicate more effort is required to understand or maintain the code. Then we have Halstead effort. It estimates the total effort required to implement the program. It combines size and difficulty to predict development time. Then we have Halstead level. It measures the program level of abstraction or sophistication. So lower levels indicate more basic, straightforward code. Higher levels suggest complex code. And then we have Halstead program time. It estimates the time to program the software based on Halstead metrics. It provides a rough measure of the effort needed for development. Then we have maintenance severity. It measures the effort required to maintain or modify the code. High values indicate code is difficult to maintain, often due to its complexity. Then we have modified condition count. It is the number of modified conditions in decision statements. It shows how many times conditions were altered, reflecting logical complexity. Then we have num operands. It is the total number of operands like variables, constants, etc. in the program. High numbers indicate more elements the program operates on increasing complexity. We have num unique operations. It is the number of distinct operations used in the program. More unique operations usually indicate more complex logic. And the last variable we have is the log total. It is the total number of lines in the code, including all code, comments, and blank lines. It represents overall program size used for size-based metrics and comparisons. So here total we have 21 features. Let's start entering them. For that, let's open test cases. Open test cases. Open the PC3 file. So these are the features that are to be given as input. So let's start entering them. We have two kinds of test cases, that is 1 and 0. So let's check with this first case where copy the log blank, paste it. Second, call pairs, copy it, paste it. Similarly, I will be entering all the values. So I have entered all the 21 features here. So here I have entered all the 21 features. Now let's click on predict defects. And this given information, it will be pre-processed at the backend. It will be fed to the train model and the train model will be giving us a prediction. So here you can see the given input is to be defective. So here we got the warning that the analyzed software module is predicted to be defective by our hybrid swarm optimized machine learning model. And this is the recommendation to review the code for potential bugs, refactor complex logic, and that is increased test coverage, considering using static analysis tools and peer reviews to improve software quality. So here, the first, software module will be defective with these parameters. Let's check with one more. So click on PC prediction again. So let's check with the second one. So let's copy the local bank, that is line of code blank. And then we have call pairs, paste it. Then we have lock code. Then we have conditional count, paste it. Similarly, I will be entering all the values. So here I have entered all the values of the second case. And now let's click on predict defects. So here you can see the model is to be defective. Here you can see the analyze software module is predicted to be defective by our hybrid model. Now let's check with the other one. Click on PC3. So now let's check with this third case. So let's start entering the values. So line of code is 5. Call pairs are 0. This one is also 0, 10, 4, 0 0.31, 2.5, 0 0.25, 1, 13, and 2, 17.83, 10.4, 1928, 1928.85, Halstead level is 0.1, 107.16. Then we have 1, 3, 16, 13, 13. Now click on predict defects. So here you can see it is non-defective. Here you can see congratulations, the analyze software module is predicted to be non-defective by our hybrid model, that is farm optimized machine learning model. And here we have to maintain your current development, that is it is giving recommendation to maintain the current development practices and continue monitoring code quality. So now let's check with this case. So click on PC3 prediction. So log blank, that is local blank is 0, 2, 0. And then we have 6, 3, 0 0.17, 3, 0 0.67, 1, 18, then 1, 30.6, 9.39, 2697, 2697.84, 0 0.11, 149.88, 1, 2, 26, 13, and 18. Now click on predict defects. And here we got the output that it is non-defective. So in this way, you can give all the required parameters of the code, that is the software code. And here it will be giving the prediction that it is whether it is defective or non-defective. And here for the given software code for all these parameters, it is predicting that it is to be non-defective. Now let's check with the graphs. So click on about. Let's see the graphs of CM1. So click on it. So here is the sample outcome graph, where on x-axis we have the target that we are predicting and on y-axis we have count. Close it. And here we have heat map, which shows a correlation between individual features. And here we have confusion matrix, where on x-axis we have predicted class and on y-axis we have true class, that is actual predictions. And here we have SHAP value, which shows the feature importance of the model interpretability. And here we have accuracy comparison graph, where on x-axis we have all the models that we have trained and on y-axis we have accuracy. And here we have FN score. So this is the FN score. And here we have recall score, precision score, and here we have running time of the model. So here we have running time of the model. Similarly, we will be having for KC1 also. So let's see it. So this is a sample outcome, heat map, confusion matrix, SHAP value, accuracy score, precision, that is FN score. Here we have recall, precision, and running time. Now let's check with KC4. So here we have sample outcome, heat map of the data set, confusion matrix, SHAP value, accuracy scores, FN score, recall score, precision score, running time. Let's check with PC3. And here we have sample outcome, heat map, confusion matrix, SHAP value, accuracy score, FN score, recall score, precision score, and running time. Now let's check with the last data set, that is PC5. So here we have model performance results, sample outcome, heat map, confusion matrix, SHAP value, accuracy score, FN score. So let's see the accuracy score. And here we have recall score, precision score, and running time. Now click on Logout. So here you have seen that based on given requirements, if we give all the requirements of the software code, we will be getting the prediction whether it is defective or non-defective. And it is done through hybrid SAM optimized machine learning framework. So this is all about the project.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.